In this video we're going to look at the differences between the delta and the Y connections. When you're connecting the three different branches of a three-phase circuit, there's two different ways that you can do it and still maintain the balanced nature of the circuit. In this left-hand option, we see that each of the, we're looking at the load side, but these could just as easily be source sides also. We see that each branch or each phase of this three-phase load is connected to the other. In other words, we've got this leg here, B, connected to here, A, from A to here. You'll notice that there is no common point connecting all three of these. On the other hand, in the Y connection, each of the three phases comes together and is connected at a common point, which we call the neutral point. So in a delta connection, there is no neutral. There's no point that is common to all three branches of the three-phase circuit. And in the Y connection, there is. Now this introduces some interesting consequences that we'll talk more about and learn how to deal with, but right now in this video we just want to point out what they are. You'll notice in the Y-connected configuration, each individual phase has a phase voltage across it, which we call the phase voltage. So we have plus to minus VAN. We have plus to minus VBN, and plus to minus VCN. But you'll notice that there is no equivalent or comparable voltage here in the delta connected side. Over here in the delta, we have only the voltage from one line to the other line, which is called the line voltage, plus to minus VAB, plus to minus VBC, and then plus to minus VCA. In other words, the voltage from line to line, which we call the line voltage, is the same as the voltage across a single phase of the load. So the line voltage and the phase voltage are the same, or they are equal. Line voltage is equal to the phase voltage. On the other hand, the voltage across the phase, VAN, whereas a line voltage, the voltage between two voltages, would be plus to minus VAB, plus to minus VBC, and then plus to minus VCA constitute the three, well, let's put it this way. VAN, VBN, and VCN all constitute a set of balanced voltages, as well as VAB, VBC, and VCA constitute a set of balanced voltages. And of course, by that what we mean is that the sum of them, VAB plus VBC plus VCA, is equal to 0. They cancel each other. And similarly, VAN plus VBN plus VCN equals 0. Over here on the delta connected load, the line voltages VAB, VBC, and VCA similarly constitute a balanced set of three-phase voltages. Notice that these points, point A, B, and C, and the points over here, A, B, and C, are equivalent points. If this load was connected to the same source that this load was, the voltages, the line voltages, VAB, VBC, and VCA, would be the same as the corresponding line voltages over here. Again, and not meaning to belabor it, but because there is a neutral point, a common point where each of these phases is connected, the phase voltage is not the same as the voltage between two lines. We'll see in the next video what the relationship is between the line voltage and the phase voltages in each of these. So, in the delta connection, the line voltages is equal to phase voltages, and over here, the line voltages and phase voltages are different. On the other hand, notice in a Y-connected load, the line current I sub little a, big A, which is the current flowing in the transmission line, goes directly and without subdivision into the phase. And similarly, the line current I sub little b, big B goes directly through the phase as well as the C. So in this situation, the line current are equal to the phase currents. In a delta connected load, that is not the case. Here we have the line current I sub little a, big A coming to a node, and then there is a separation. We're going to define the phase currents in the delta connected load as I sub AB, the current flowing from node A to node B, the phase current I sub B to C, I sub B, C, and then finally the current going from C to A, I sub C A, as the three phase currents. And you'll note that the phase currents are not the same as the line current. And if we define these phase currents in this way, it is true that I sub AB plus I sub BC plus I sub CA equals 0. In other words, those three currents, as assigned or as defined, represent a balanced three-phase set. It's also convenient to understand and not define, but calculate, I guess, derive the relationship between the impedance in a delta-connected load and that in a Y-connected load. You'll recall from a long time ago when we were looking at delta and Y conversions, we saw that the Y-connected impedance, we called them Z1, was equal to Z sub B, Z sub C over Z1 plus Z2 plus ZA plus ZB plus ZC. In other words, the Y-connected load value could be determined from the delta-connected values Z sub B, Z sub C over ZA, B, and C. So this was ZY. Now, in a balanced three-phase system, the delta-connected impedances are all equal. So we would have then, and I'll just call it Z delta times Z delta over Z delta plus Z delta plus Z delta. And so you get Z delta squared over 3 Z delta. That leaves us then Z delta over 3. Thus, when you're taking a delta-connected load and want to convert it to a Y connection, the individual Z sub Y's, of which there are 3, one for each phase, that's a Y, each of these will equal 1/3 of the delta-connected load. We're going to see, and we've got an example out there, that in analyzing circuits with delta-connected loads, the way we're going to do it is convert them, or at least one way we're to do it, is to convert the delta-connected load to the Y-connected load, which then introduces a neutral. It's an equivalent circuit. It introduces a neutral, which then allows us to evaluate the three-phase circuit by looking at just a single phase. And once we know the quantities in the single phase, we can then infer the quantities in the other two phases by simply adding or subtracting a 120-degree phase shift.